Welcome to this explainer. Today, we're diving into the literal brains of your computer to look at the incredible traffic control systems inside modern CPUs. We're going to break down the meticulous mechanisms that keep instructions flowing smoothly without bottlenecking the whole system. It's a really fascinating journey into the heart of computer architecture, and we'll be specifically focusing on how processors overcome internal roadblocks using two main techniques: static and dynamic scheduling.
But before we get into the technical weeds, I want you to consider a pretty fundamental question. How exactly does a processor execute billions of calculations per second without constantly, tripping over its own feet? Think about a massive, busy city intersection. Without traffic lights, roundabouts, or traffic cops, it would just be absolute gridlock, right? Well, your CPU faces that exact same problem with a constant stream of data and instructions it needs to process. And the way it solves this is exactly what makes your laptop or your smartphone feel so incredibly fast and responsive.
So here's our agenda for today. 1. The instruction hazard problem. 2. Static scheduling and compiler control. 3. Dynamic scheduling and hardware control. 4. The power of speculation. And finally, 5. Modern processor architectures. Let's get into it.
Starting off with Section 1, the instruction hazard problem. Think of the instruction pipeline like a highly efficient factory assembly line. Instructions have to flow sequentially through specific steps. You've got IF for instruction fetch, ID for instruction decode, EX for execute, MEM for memory access, and WB for write back. But here's the catch. Dependencies between these instructions create what computer scientists call hazards. You've got structural hazards, data hazards, and control hazards. Essentially, when one instruction desperately needs the result of another instruction that hasn't actually finished yet, the pipeline has to stall. The CPU literally has to hit the brakes. To overcome these stalls and keep that data flowing, computer architects basically split into two distinct camps, developing two different philosophies. The first one is static scheduling. This is a purely compiler-based approach. The software compiler acts as this ultimate master planner. It analyzes the code and schedules the instructions long before the program actually runs, with the goal of avoiding those hazards entirely. Then there's the second philosophy, dynamic scheduling. In this approach, the physical hardware itself steps up to act as the live traffic controller. So instead of relying entirely on a pre-planned route, the CPU figures out the dependencies and schedules instructions on the fly, right while the program is actively running. It's the classic computing debate, really, preparation versus adaptation. When you weigh these two side by side, you've got the software meticulously pre-planning its route at compile time on the one hand, versus the hardware adjusting dynamically to live traffic conditions at runtime on the other. Both approaches absolutely want to eliminate pipeline stalls. They just go about it in completely different ways. All right, Section 2, static scheduling and compiler control. Under static scheduling, the compiler is essentially a meticulous puzzle solver, and it uses some pretty sophisticated techniques to pull this off. There's loop unrolling, which basically expands iterative loops to expose way more instruction-level parallelism. There's also software pipelining. And then we have trace scheduling, which is super cool. It organizes instructions along the most frequently executed code paths, so it's optimizing the route it thinks the program is going to take most often. Finally, there's superblock scheduling. But remember, all of these rely entirely on software foresight. Moving right along to Section 3, dynamic scheduling and hardware control. To actually achieve this on-the-fly flexibility, the hardware does something really clever. It splits the instruction decode stage into two distinct steps. First, it issues the instructions strictly in order. That's crucial to keep track of the program's original intent. But step 2 is where the magic really happens. It waits to read the operands and execute out of order, acting precisely at the moment the required data is finally available. This completely bypasses those pesky true data dependence stalls. Now, a massive historical breakthrough in this out-of-order execution space was Thomas Solo's approach, which was initially developed for the highly influential IBM 360/91. Thomas Solo's algorithm brilliantly renames registers using what are called reservation stations. By doing this, it completely bypasses false data hazards, specifically anti-dependencies and output dependencies, without needing to stall the pipeline at all. It effectively creates these temporary, isolated workspaces for instructions so they don't accidentally overwrite each other's data prematurely. So we can trace a pretty clear evolution here. Basic dynamic scheduling is a great start. It handles data hazard stalls from true data dependencies. But when you upgrade to advanced techniques like Tomasulo's approach, you are effectively eliminating stalls caused by anti-dependencies and output dependencies too. The hardware is literally untangling the traffic jam in real time.
Which brings us to Section 4, the power of speculation.
What if the processor could just guess the future to avoid stalls entirely? Well, hardware-based speculation goes way beyond just scheduling available instructions. It actively predicts the outcome of branches in your code. It fetches, issues, and actually executes instructions speculatively, acting as if its prediction is 100% correct. But obviously, it needs a safety net. So it holds these uncommitted, speculative results in a hardware structure called a reorder buffer, or ROB. Once it actually confirms the prediction was right, then it commits the instructions in order to the permanent architectural state.
But the million-dollar question is, what happens when it guesses wrong? Or what if a sudden system interrupt occurs? Well, because the speculative results are held safely in the reorder buffer, the CPU simply flushes that buffer. The speculation is cleanly undone without corrupting the permanent state of the machine at all. This is a massive advantage because standard dynamic scheduling without speculation just couldn't safely back out of executed instructions if an interrupt occurred. Finally, Section 5. Modern processor architectures. When we're looking at processors capable of issuing multiple instructions per cycle, they generally fall into two architectural buckets. On one side, we have superscalar processors like the famous Intel Pentium series. These try to utilize the best of both worlds, relying on the compiler for static scheduling, but also packing some seriously heavy hardware for dynamic scheduling and speculation. On the other side, we have VLIW, or Very Long Instruction Word processors, which rely almost purely on the compiler's static scheduling to find that parallelism. In a VLIW processor, the compiler is doing all the heavy lifting up front. It analyzes the code and bundles multiple independent operations into one single, very long instruction word. So by the time the instructions actually reach the hardware, the explicit parallelism is already perfectly packed in. This completely offloads the massive complexity of dynamic scheduling straight to the software. When you bring all these technologies together, the compound effect is just wild. Dynamic branch prediction dramatically reduces control hazard stalls. Speculation reduces both data and control hazard stalls. And finally, combining all of this into architectures that can issue multiple instructions per cycle drives our efficiency forward, constantly pushing for that optimal, ideal cycles per instruction metric. So, as we inevitably hit the physical limits of just how small, hot, and fast we can make these hardware pipelines, I want to leave you with this to consider. If we can't just keep throwing more hardware prediction and speculation at the problem indefinitely, what is the next great leap in traffic control for the processors of tomorrow? Are compilers going to get drastically smarter, or is there an entirely new dynamic scheduling paradigm just waiting to be discovered? Thank you so much for joining me for this explainer. Keep wondering and keep learning.